Welcome everybody to this, it's not number 8, but it's 8 years that we're doing this at the Academy of Sciences, the Avond van de Abelprijs, the Abelprijs evening. This year's winner, Masaki Kashiwara. Before we start with 3 distinguished speakers who are specialists on the work of this broad and versatile and productive mathematician, I thought it's nice to take you through a few slides about the Abelprijs. So my name, by the way, is Jan van Eerven. In daily life, I'm professor of analysis at the TU Delft. And so why an Abelprijs? Well, it's a prize established in 2002 on the bicentenary of Abel. For outstanding scientific work in the field of mathematics, and the prize is awarded by the Norwegian Academy of Science and Letters. This year's winner, already mentioned, Masaki Kashiwara, you've probably also seen it on the leaflet, got the Abelprijs for his fundamental contributions to the algebraic analysis and representation theory, in particular the development of the theory of D modules and the discovery of crystal graphs. What all this is, we hope to learn tonight if our 3 speakers will highlight various aspects of Kashiwara's work. I want to tell you a little bit about the Abelprijs. It's considered, as you know, kind of a substitute, if you like, for the Nobel Prize, which we don't have in the area of mathematics. And there are famous, say, tabloid-like stories why that would be so. This is taken from a nice small paper in the Mathematical Intelligencer by Garding and Hermander, who wrote about it. And you see it on the slide, so there are 2 versions why there's no mathematics Nobel Prize. The first is the French-American version. Mieter Leffler, a Swedish mathematician, had an affair with Nobel's wife. This is, of course, debunked, but the story is juicy nevertheless. And the Swedish version is that Mieter Leffler was the leading Swedish mathematician at the time when Nobel wrote his will. Nobel knew that if there was to be a prize in mathematics, Mieter Leffler could use his influence in the Royal Swedish Society Academy of Sciences to become the first recipient. To avoid this, Nobel gave no prize in mathematics. The true story is a bit more subtle. It has to do with his will, which comes in several versions. The original version from March 14, 1893, established an annual prize, quote, for the most important and most pioneering work in the wide domain of knowledge and progress. Now, that by itself would not exclude mathematics, obviously. But then in the final version, dated 2 years later, he was very specific about to which areas the prize should be awarded. And as you know, these are 5 areas, and later economics was added to that. And basically it's to those who during the past years have done mankind the greatest good, and then there's a specification of the prize. And then, of course, it's a realm of speculation why he singled out those. But he was a practical man. We know him from the invention of dynamite, and probably the good of mankind was more tangible than our say, mathematical fancies of the mind, which we call mathematics. Then the idea then to come up with an alternative to the Nobel Prize for Mathematics is due to Sophus Lee, who proposed that one could install a prize on Abel's centenary in 1902. But okay, that should be 1899. Lee died, and that was just before things actually could get going. But then what came in between is a political turmoil, which then ended up in the separation between Sweden and Norway in 1905. And I found a nice internet picture of the dissolution negotiations that took place in that year. So then, in the end, the prize never happened. And then, with the advent of the bicentenary in 2002, the Norwegian government then finally established an Abel Fund to finance this prize. And ever since, we have had this. And it was in 2018, if I'm right, that the Academy took up the idea to have an annual lecture One could, of course, take the Fields Medal, but that's only every 4 years, and much nicer to have this as an annual event. So the Abelprijs was singled out for that purpose. And 2018, I think, was the first edition with Langlands, and then we had various. It wasn't every year due to COVID, for instance. So there have been a few gaps in the sequence, but this is number 6 or 7. Okay, so that's really what I have to say. I think it's time now to introduce the speakers. Gert Hekman from the Radboud University in Nijmegen, Yajnaseni Dutta from Leiden University, and Raf Bocklandt from the University of Amsterdam, all distinguished speakers in the various aspects of Kashiwara's work. So to introduce Gert Hekman. Gert Hekman is a specialist in symplectic geometry and representation theory and various areas in between. Distinguished mathematician, emeritus professor since 6 or 7 years now, yes. And he's only, say from the 3 speakers, the one who in person met Kashiwara several times. We could read in the newspaper, in the NRC, there's been an interview with Gert about the awardness of this prize. So there we learned that they met in Paris in Café L'Epsilon, which is very fitting, I think, for mathematicians, a place to meet. And what they discussed there, I think we're going to hear now from Gert. So please, the floor is yours.
Yes, so Kashiwara got the Abelprijs for his actually 2 things, his work on the Riemann-Hilbert correspondence and another topic in the representation theory. But I was asked to tell something about this Riemann-Hilbert correspondence for a sort of general audience, which is not so easy because Kashiwara is technical. It is hard mathematics. He speaks various languages, algebraic geometry, Grothendieck style algebraic geometry on the one hand, and then the Japanese algebraic analysis, hyperfunctions, and so forth. So I want to say something about 4 people. I will start with Kashiwara, then a little bit about Hilbert, because it occurs in the name, and then I will talk about Riemann most of the time, because that is something which I can explain in quite easy terms. The theorem he proves in 1984 is that there is an equivalence of the derived category of holonomic systems and that of constructible sheaves. Well, that's a very technical statement, but a holonomic system is a system of partial differential equations. And systems of differential equations you can write down algebraically, maybe geometrically. That is relatively easy. The hard part with differential equations is the solutions. And then for a particular kind, these holonomic systems, you can not write down the solutions, but using solutions, you can derive certain topological consequences. And in the end, it turns out that these are the constructible sheaves, that the topology characterizes the differential equations. The topology is relatively simple and the differential equation complicated. It is beyond my capacity to go into that proof, and I think for most of the people in the audience it wouldn't be possible either. He, as an application of that work, he was able to solve with Jean-Luc Brilinski in the early 80s, the Kasdan-Lustig conjecture about the structure of the irreducible representations of real semi-simple Lie groups. Hilbert, the Riemann-Hilbert problem. In 1900, Hilbert gave a lecture in Paris. In that lecture, he discussed the relevance of good problems for the development of mathematics. If there are no problems, not enough problems, mathematics will be extinct in the end. So he presented a list of 10 problems, and later in his lecture he expanded them into 23 mathematical problems, and it's a very famous list, and if you can solve one of these problems, you become famous as well. This is what Hilbert formulates. I want to indicate an important problem, one which very likely Riemann himself may have had in mind, to show that there always exists a linear differential equation of the Fuchsian class with given singular points and monodromy group. So let me then go to Riemann. I will discuss two papers of Riemann from 1857. One is an example, and that's the hypergeometric equation. And there, if you understand the example, then it's sort of natural to understand the general problem. The hypergeometric function, that's the function f alpha beta gamma x, is a solution of that hypergeometric equation. It's a second order linear differential equations with, well, if you divide the leading coefficient, it has a rational coefficient. It's an algebraic differential equation, linear. One of the simplest kind of differential equations. Nevertheless, solutions have interesting aspects. And then the first point, well, by the way, I wrote that Riemann was born in 1826, which means that one other reason for talking today a bit more about Riemann is that it's 200 years ago he was born. The first remark Riemann made before him, as you see in the title, there is the variable is x, and then in the differential equation I wrote down it is z, and so z is now complex. That is extremely important because, as Riemann wrote 6 years before in his inaugural dissertation, if you allow for these problems the variable to become complex, you can see a harmony and regularity which otherwise would remain hidden. And that is exactly what we will see. So z is a variable, it's a complex variable, and then we add a point at infinity, and then I'll denote by p, it's a projective line. The differential equation has 3 singular points, 0 and 1. It's that factor in front, z times 1 minus z is 0, and at infinity it also has a singular point. Outside those 3 points, locally around a point, around a point z, you can prescribe unique holomorphic solution if you give the value and the first derivative. And that varies with the point z, and I will call that a local solution system, a local system of holomorphic functions which varies over the complex plane minus 0 and 1. And then, so the essential point is the 3 singular points. For example, near z is 0, you can substitute the solution of the form z to the power s with exponent s times a holomorphic function, and then if you substitute it in the equation, you get a quadratic equation in S, which has solutions S is 0 and S is 1 minus gamma, and the solution corresponding with S is 0 is the hypergeometric function, it's a power series, and the other one starts with z to the power 1 minus gamma, and you can do something similar around 1 and infinity, and you get these, well, this little table is called the Riemann scheme of local exponents at the 3 singular points. And you may remark here that the sum of the these 6 exponents is equal to 1. We'll see that later, that it plays a role. Well, the picture one should have in mind is what I draw over there. Well, maybe first the theorem. The hypergeometric local system characterizes, well, it is uniquely characterized as a system of holomorphic functions on projective line minus those 3 points, given the local exponents. And moreover, he introduced an invariant, he called it the monodromy. If you take some point, say point 1/2, and I call it Z0, some base point, the fundamental group is the group of loops up to deformation. You can give it a group structure, and it is generated by loops around 0, 1, and infinity, and the relation is that the product of those 3 is 1. And what you then get is a representation of that fundamental group on the local solution space at the point you are taking, at the point Z0. Call that space V0. It's just a two-dimensional complex vector space. And the monodromy is computable, although you cannot compute those functions. Well, you can find power series, but there is this global thing you can compute called the monodromy representation. It's a subgroup of the group of linear transformations on that local solution space V0, and it is generated by the monodromy around 0, 1, and infinity, and those matrices have eigenvalues. Well, for example, M0 has eigenvalue 1, and 1/c, which corresponds exactly as we saw here in the Riemann scheme. You have local exponents 0 and 1 minus gamma. And the theorem of Riemann is that the monodromy group is the unique subgroup of GLV0, generated by 3 matrices, satisfying these properties on the left, plus a property on the right, which is topological. The product of those 3 matrices is a reflection of the relation we saw in the fundamental group. Okay, it's, I think, very important to understand this example. Riemann wrote a paper about it. He thought it was important enough to write this in a paper. Well, why the hypergeometric function is important? Today, well, it's important for problems in mathematical physics. I don't know whether Riemann really, whether that was his motivation. It had been studied in the century before by Euler and Pfaff and various other people. And I think you have the Euler integral, and so for rational parameters, alpha, beta, gamma, it's an example of what is called an abelian function. And probably that was the more important reason for Riemann to study this equation, this example in detail. Okay, so now I come to the second paper. The second paper is unpublished, but in his collected works, it is Abhandlung 21. So it's funny that Riemann also called his problem the 21st Hilbert problem, because it's also in the 21st paper of his collected works. And now the picture is as follows. You have, so you want to generalize this to more singular points and higher order linear differential equations. So suppose you prescribe a set S of singular points, Z1 up to Zn, and also Zn plus 1. Let's put it in infinity. Suppose we have a local system on the complement of those points of holomorphic functions of rank n. So locally it's an n-dimensional space of holomorphic functions, and you can move that local system around as long as you stay away from the points, the singular, the candidate singular points. Suppose you prescribe a Riemann scheme, that is, at each of those points you give n local exponents. At the point Zj you have alpha 1j up to alpha nj. You prescribe them freely. We have the fundamental group. It's generated by loops around all those singular points with the same relation. And the monodromy around the point Zj has eigenvalues. Well, e to the 2 pi I times alpha ij. It's just, so there's a compatibility between the Riemann scheme of local exponents and the eigenvalues of the monodromy around the singular point. Well, the first theorem in that paper is that if you have such an abstract given thing of a local system of holomorphic functions with these conditions, then those functions are solution of a differential equation. And that's actually very simple. You consider an n plus 1 by n plus 1 matrix. The first column is a general solution, and then you have the basis f1 up to fn. And then you make that matrix that you take the second row is the derivative, and so forth. And the last row are the nth derivatives of the general solution f and the other. And because the first column is a linear combination of the others, the determinant is 0. And if you expand the first column, then you have your differential equation there. So the delta 0, for example, is the Wronskian. You just delete the first column and the last row. And then you remark, by looking locally at the points, that if you multiply by a suitable factor given the local exponents, you can transform the differential equation into one with entire coefficients. The coefficients are globally holomorphic over the plane, and in fact, these coefficients a, k are of the form bk divided by omega to the k, where omega is the polynomial which vanishes at the singular point z1 up to zm. It's all very easy to conclude from that form. And the bk is now holomorphic. And then you do an analysis at infinity, and then what you see is that in fact, the bk, well, first of all, you have this front coefficient a0. You don't know much about that, except it's entire and shouldn't, well, it should be a polynomial. That's what you can also deduce because of the behavior at infinity. You cannot have problems at infinity. Let's assume it's of degree r with distinct zeros, w1 up to wr. And then in order that the equation is regular singular, you have this estimate on the coefficients bk, which are of that form over there. So you have additional singularities besides the prescribed singularities z1 up to zn plus 1, namely these w1, but at these points you have no monodromy. These functions are just holomorphic. And so in the monodromy you don't see them, and we call them apparent singularities. Well, you do a moduli count. This is what Riemann, in various of Riemann's papers, he did a moduli count, and he does it here as well. So you can easily count the number of parameters in those differential equations. You can also count the number of parameters in monodromy representations. That is very easy. You can prescribe matrices m1 up to mn, each n by n, so you have m times n squared, but they are unique up to conjugation. So you have to subtract n squared minus 1. You also can check that the number r of apparent singularities plus the total sum of exponents is equal to a certain number. Well, so just simple checks. And then the final result is that in order that for an arbitrary monodromy representation such a differential equation exists, you want that to have more parameters for differential equations than for monodromy representations. And that turns out to be equivalent to S, the sum of exponents at the singular points from S, S at most equal to n minus 1. So for example, if S is equal to n minus 1, you have an equal amount of free parameters for representation as you have for differential equations. For the hypergeometric equation, we have three singular points, and the S there was 1, which is, so the R then in that case is equal to 0. Easy to check from those formulas that if the number of singular points is at least 3 and the order is at least 2, the only case where you have such differential equations without apparent singularities is in fact the hypergeometric equation. So it's really the example par excellence to understand the Riemann-Hilbert correspondence. Okay, my final slide. It was solved for the first time in 1908 by Joseph Plemel. And what he did, well, you have that linear nth order differential equation. You can easily rewrite that as a first order matrix system. And in that language, things become easier. And he solved it in that context. Then, in 1970, the linear proved an extension of this theorem that about the equivalence of modular representations and those systems of differential equations. He extended it to the case of several variables. In the Springer lecture notes, équation différentielle à point singulier régulier. And that proof is, once you understand, so he transforms it again in a slightly more abstract language of vector bundles of rank n with flat connections. And the proof is truly amazing. It is between working in the analytic setting and the algebraic setting, and the equivalence of that. There's a theorem of Jean-Pierre Serre. It's a Gaga principle. Under certain conditions, if you have done a construction in an analytic setting, it works. It is in fact an algebraic construction. Okay, finally, Kashiwara and Mapkut, Mapkut proved independently of each other an extension of this result in the D module setting. So in fact, they return to the case of higher order linear differential equations. And this was all I wanted to say.
Thank you very much, Kat, for this interesting talk. There's time for questions. Yeah.
So the two theorems that you refer to in your last 1984 time window, they're exactly the same?
The theorem of Zokman-Mapkut and Kashiwara.
Yeah.
I think they, generally speaking, it's considered that they did the same problem. I'm not really the person to judge that. I know that Grothendieck took really a stand-up for Mapkut in his récolte essay Maya, that he was not appreciated well enough. Last Saturday I was with Jozef Steenbrink, who's an expert also on these things, and he said they proved the same theorem. So I believe Jozef is an expert, and I think the answer is yes.
Are the proofs very different?
Well, I must say I don't know, because I didn't read those proofs. The proofs are both only readable if you are an expert in Grothendieck algebraic geometry. So I worked myself in representation theory and in examples of that correspondence, applied it several times. I was in '87 in Paris, and I was giving lectures on hypergeometric functions. And there was a series of lectures. In the first lecture, I talked about the classical hypergeometric function. And then after the lecture, somebody came up to me, it was Zokman-Mapkut, And he said, well, that's interesting, yeah. No. So I knew the name from the Riemann-Hilbert correspondence. He said, I never knew what the hypergeometric function was. So I thought it was quite funny. There are these people who do these utterly abstract general things without knowing the examples where they come from. And I just worked the other way around.
Interesting. Any other questions? That seems to be not the case. If you then later realize, oh, I should have asked this question, then there will be the panel discussion later on. You get a second opportunity. For now, I thank Gert again. And then it's my pleasure to introduce our second speaker, Yajnaseni Dutta from Leiden University. She did her PhD in Northwestern after finishing her studies in India, I think. And then a postdoc at Hausdorff Institute in Bonn, and now since a couple of years she's in Leiden. So Yajna, the floor is yours.
Thank you very much. Thanks very much for inviting me to this wonderful evening and for giving me the opportunity to talk about Professor Kashiwara's work that has also influenced my own research journey by a lot. I was asked to talk about D modules, and I decided to go back. We have to go back about 14 years earlier from the previous talk. I wanted to talk about his master's thesis. So already in his master's thesis, Kashiwara was working with D modules, which are cornerstones of this field that's known as algebraic analysis now. So the founder of algebraic analysis, one of the founders of algebraic analysis was Professor Mikio Sato. He was Kashiwara's advisor, master's advisor in 1970. And already this is probably one of the earliest results that Kashiwara proved, and already there he took a century-old problem in real analysis and turned it into a very simple, elegant algebraic statement, a statement which is just bijection between two sets. So this is why I chose this topic, because this is also one of the first things I learned when I was learning about D modules as a graduate student. So, this is when he wrote his master's thesis in 1970, he wrote it by hand in Japanese, and this was. Mathematicians soon understood that this is a very important result, and his thesis was being distributed around just by making copies. It was only 25 years later that his thesis was finally translated in English. And in the foreword, it was translated by Professor Danello. And in the foreword, written by Pia Shapira, he writes that as it will become clear, as it will become evident to the reader, the thesis could have been written last week, modulo minor modifications. It contains a great deal of little known or even unknown results that could be used almost without any changes as a textbook for postgraduate students. So I think this. So to talk about what these results are, I think I would like to start from the very beginning, from the story of differential equations. So when mathematicians and physicists were studying the phenomena of physical motion, particle motion, we soon realized that it's sometimes the only data that one needs to care about is not the position of a particle, but how it's changing. So pictorially and informally, this is captured by diagrams like that are commonly known as slope field diagram, which dictates at every point of the space where should the particle move. So these small lines are supposed to indicate which direction the particle should be moving at every position. So it's kind of believable that if I tell us that the particle should start from here, it has to go in this direction, and its path is sort of immediately fully determined. So these kind of statements are usually written in terms of linear differential equations. So and the fact that its path is completely uniquely determined is a classical theorem of Picard-Lindelof, which states that given a differential equation, du dx equals fu for some real analytic function f, so this is basically giving us the prescription, so the function fu is giving the prescription of how the position, which is u, changes with respect to some influence x, right? This theorem states that then there exists a unique real analytic solution once we fix an initial condition. So once we fix where the particle starts its journey, then its path is fully determined. So the existence and uniqueness part, from what I understand, is Picard-Lindelof theorem, and Kovalevskaya's name comes in because of the fact that the solution is real analytic, which just means that the path is as nice as you can expect. There's no corners. It's infinitely differentiable. But of course, not all motions are as simple as that. It's a bit, it's a bit deceiving to think that. So already in everyday life, when we throw a stone upwards, we experience differential equations that are more complicated than this already. Basically, if you throw a stone upwards, you are fixing its initial position and you're fixing its initial velocity. However, gravity acts, so the velocity that goes upward kind of starts changing, and then eventually it stops and then starts falling to the ground. So even so here, what's most important is that how the change is changing, right? Like how the change of motion or the velocity is changing. So as you can see in this little demonstration, that if my stone starts from 0, 0, starts flowing upwards, its upward velocity is being affected by the gravity, and then it stops. But as I said, that if I specify where the particle begins its journey and how fast it goes, how fast you throw the stone, already determines its entire path. So this can be, in order to write this situation, we need a differential equation of order 2. Just to reiterate, the differential equation, if I wrote it, it would look like derivative d2u over dt squared is equal to the gravitational constant. And you should think of this u as the position of the particle in the vertical direction. And the initial conditions here were, I fixed the initial position where the particle began its journey and the initial velocity, or how fast I threw it. Okay? But of course, one can imagine from here on that not every situation is as simple as a first order or a second order differential equation. For instance, there may be many variables affecting trajectory or whatever we are trying to study. There may be variables, 2 variables or more. The differential equation might look more complicated. It might have much higher order. For example, we may be interested in how a change is changing, or how change in one direction gets affected by change in another direction, or very, very deep changes, right? We may be interested in initial conditions. So here, when we have many variables, the initial condition that I will be interested in is, what if I set one variable to 0? Okay, so I want to, the initial conditions should tell me everything about this situation. In particular, it should tell me what function dictates once I set one of the variables to 0. So my desired solution is u, and if I set the variable y to 0, I should know everything. I should know how the function u behaves. So this gx is the function in all variables other than y. It's an analytic function. It tells me how u should look like if I restrict it to all variables other than y. Similarly, I should know, if the equation has order 2 or more, I should know its initial velocity, just like the stones when we threw the stone. And if the differential equation is even more complicated, has even more higher order, then I should know everything until the maximum of these of this sum minus 1. Okay, so I should know all the changes up to the final one that the differential equation wants to solve. So this number is something that we will refer to later on. So let me give it a name. it's called order of the differential operator. It's given by the maximum of this exponent that shows up here. For example, if I take this made-up differential equation, then the maximum here is 4. Then the order here is 4. The order of the operator here is 4. Here it's 3. So the order of this entire differential operator is 4. Okay. Now initial conditions. So I would like to think, since the initial condition is a bit more complicated here, I would like us to think about this a bit more geometrically. It's perhaps a bit easier to understand. So setting one variable to y to 0 can be, you can think of, if I'm, say, working with 3 variables, then this is setting one variable to 0 and knowing everything about it is the same as knowing the value of the function and the derivatives on this hyperplane. Okay, so this is the collection of all points whose y-coordinate is 0. So once we have this geometric intuition, why not make it more general? We could consider much more complicated hypersurfaces and ask a similar question that, let's say, I know everything about, the initial condition tells us everything about restricting the differential equation to this hypersurface, then can we solve it? That's the question we are asking. So once the differential equation becomes so complicated, whether or not a solution exists also becomes a harder question. So this is the question that one can ask, that does this equation have a solution? If it exists, is it a unique solution? And whether it is analytic or not. Okay? The Cauchy-Kovalevskaya theorem, so about 100 years before Kashiwara's thesis, gave an answer that yes. So if you look locally, then there exists a unique solution to the differential equation pu equals 0. So here this p is just a symbolic way to write this complicated summation that was in the previous slides, where p is an order R differential operator. Once we fix the initial conditions given by setting one variable to 0, and all the derivatives up to the order -1. Okay? This is not completely true. It is modulo some assumption on how the differential equation interact with the hypersurface. So P must be non-characteristic with respect to the hypersurface. Okay. So this is a purely analytic statement that was proven about 100 years before Kashiwara's thesis. Let me take a small detour and say a few words about Sofia Kovalevskaya, who was Sweden's first female professor. And in one of the biographies, she says, "It's impossible to be a mathematician without being a poet in spirit. It seems to me that the poet must see what others do not see, must see more deeply than other people, and the mathematician must do the same." And I think Kashiwara did just that. He reproved Cauchy-Kovalevskaya's theorem, so I want to describe for the rest of my talk some words about his proof, or at least like the reformulation of the statement. So the key idea behind his reformulation was that what is better than one solution? Well, it's all solutions. So let's denote the set of all solutions to the differential equation pu equals 0 by this symbol. I'll come back and explain this in a second. I just want to state it, so let's take this to denote the set of all solutions of the differential equation, and let's take this other symbol to denote all the initial conditions set by restricting the differential equation to y. Okay? Then what Kashiwara proved was that these two sets are bijective to each other. So what that means is that if I'm given a set of initial conditions, so something on this side, then there's a unique element that maps to it. And if you believe that this is the set of solutions, then this theorem immediately tells us that the solution exists, it's unique. And if we know a bit more about this, it also tells us that it's analytic. So this is the beauty of Kashiwara's statement. So now I want to move on to explain what these notations mean and look back at this statement. So there's the most recurrent symbol here is D. So let me explain what that is. So this is what I said in words, that as soon as we have something on the right-hand side, such a solution exists, it's unique, and it's analytic. Okay. So what is D? So this D, a priori, is just a set. It contains all analytic functions. It contains all partial derivatives, just as operator. Abstractly, it's not deriving any function, just there. And and all the higher order derivatives, and so on. Okay. So a priori, it contains at least these elements, but then it's also dictated by the rule that if you have two operators, P and Q in D, then its sum must also be in the set. So we can add elements in D. If you have two elements in two operators, differential operators in D, we should also be able to compose them, right? So here, for example, if I take del x and del y, I compose them, I get this element. Okay? So that's composition. But furthermore, if you take any two elements, you should be able to compose them, and we can then think of this composition as a multiplication. And together with 0 and 1 as analytic functions, this makes D into what we call rings. Okay. So the elements of this set is what we will call differential operators. And now, so this is just an abstract set of some operators, but what are they without acting on something or deriving some functions, right? So the set on which these differential operators will act will be called D modules. A D module is a set where differential operator acts. So the first example of D module will be the set of analytic functions. So analytic functions are something that you can derive over and over again. So if you derive an analytic function, it's analytic again. So it's an example of a D module. The ring D itself, as a set, you can act D on the ring. So it's a D module itself. Then another thing that will be interesting to us is when if we fix an operator P, then the left ideal generated by this operator P is again a D module. So it's by that I mean all element that can be written as Q times P. Okay, so D also acts on this set, so this is also a D module. Furthermore, if you have a submodule of a D module and then you quotient it, then that's also a D module. So the one that we will be particularly interested in is D mod dP. One way to think about it is to think of a clock where every time you hit 12, you are reset to 0. Here we should think of P as the one that's acting as 12. So every time we cross P, we start again from 0. So in particular, P is 0 in this D module. So that's very important. That will be very relevant in a second. Okay, so now let's look back at Kashiwara's statement, and let's try to understand both sides of the bijection. So let me try to convince you that this left-hand side is the set of all solutions. So how do we see that? Well, here HOM stands for D module homomorphisms. So we have two D modules here, D mod dP and the set of all analytic functions. And this HOM is all maps, all assignments from left to right, which preserves the D module structure. Okay? So maybe let's look at something simpler. HOM D of D comma O. So these two are D modules. So this is like the set of all homomorphisms, D module homomorphisms from D to O. And I claim that this is isomorphic to O, set of all analytic functions. So briefly, how do we see that? Well, if we take an analytic function U, then this prescribes a way to go from here to here, namely by, if I take Q here, then I can derive the function U to get an analytic function here. And what's interesting is that you can reverse this process, and this is an isomorphism of O, basically, of O modules. Okay, that's, these two sets are isomorphic. So it's not hard to believe then that if I now, instead of mapping from D, if I map from something where P is 0, it should correspond to the set where where PU is 0. The action of the differential operator acts as 0. So that is exactly what we are looking for. This is exactly the set of solutions. Okay. So now let's move on to the right-hand side, and let me explain to you why the other set is the set of initial conditions. So, here we have a slightly different symbol, namely dy. So dy is again d, nothing but d. It's just d with one less variable, namely the variable y, del y, the operator del y, or its powers won't be there. Okay. So if I restrict the original set onto y, it's perhaps slightly easier to believe that this is the set of initial conditions. So let's look at this quantity and see what it is. So if I restrict the d mod dp to y, if p is non-characteristic with respect to y, then this restriction will be exactly all the differential operators that in all variables other than y, and all differential operators together with del y, and so on until the order, until our order of p minus 1. Okay. So if you believe this, then it's not difficult to, it's not difficult to see that the set of initial conditions, namely the dy module homomorphisms from here to here, will be nothing but direct sum of this, this homomorphism, the dy module homomorphism from dy to oy, and we've already seen that this set is the set of analytic functions on y. So let's look back at Kashiwara's statement once more. If we assume these technical conditions on P, namely non-characteristic at the hypersurface Y, then what Kashiwara's theorem telling us is that if I take a function u here and I send it to u restricted to y, its derivative, first derivative restricted to y, the hypersurface, and so on until the order of the differential equation minus 1 restricted to y, then this is an isomorphism. And we have seen in the previous slide that this is equal to the set of all initial conditions. Okay. So now let me pause for just a moment and just let's just marvel at this amazing statement that that basically tells us that now there's a lot of possibilities. Why stop at this particular D module? We can replace this with any D module, any arbitrary abstract D module, and we will still have an isomorphism given the differential equation is given this non-characteristic condition is satisfied. So this led to a vast generalization of the statement from real analysis that we started with, and perhaps one of the most modern way to state it is in terms of the derived category of D modules, which says that if you take any closed subspace of a space, then any complex of dy modules can be realized as a complex of dx module with support along y. Okay. So this opens the door to studying, completely repurpose this origin story, and now basically, for example, this can be studied when we want to study differential equations on y in order to understand properties of y. If y itself is too complicated, maybe we want to embed it in something nice and smooth like x, and then study the whole problem on x instead of on y. And then Kashiwara's theorem tells us that we don't lose any data by doing that. So this is, in this context, the way we went is that we were looking at physical motions, which was best explained by differential equations that was made abstract into spaces of operators, namely D modules. And now D modules is used in these various fields of mathematics that a priori are completely faraway fields like geometric Langlands, representation theory, perhaps symplectic topology here, Hodge modules, and singularities. And all of these fields are now coming back together to explain symmetries in nature. So I want to philosophize a bit more and just say that this is how probably mathematics works, that it gets inspired, it abstracts, and then it returns. Here I want to end the talk with a a short clip from the video that was made after the Abelprijs winning of Professor Kashiwara. And then here he refers to a field that's called Hodge modules, and he says that it's too complicated. But it only goes to showing that how his work has, especially on not just this result, but also his work on regular holonomic D modules, has done all the groundwork. It made it fertile to Hodge modules to sprout and be its own thing, while Kashiwara was busy proving other results. So
yeah, for example, that is when I started the so-called mixed Hodge modules. Those are the rather complicated stuff, and I can't remember anymore. They are completed by Morihiko Saito, but it's not easy to follow now.
With this note, I would like to end my talk. Thank you very much.
Thank you very much, Yajna, for this very nice talk. Let's see if there are any questions. Yes.
Thank you very much for your talk. Very interesting. So one question I had is you mentioned this one technical detail which we keep assuming for the entire process. Could you maybe, non-characteristic, I think you said, could you maybe explain what that means?
So I'm going to say something that's not completely true, but roughly speaking, in this context, if I'm restricting to y equals 0, it would roughly mean that the rth derivative with respect to y must be present in the differential operator. But in general, one can define it in terms of, it's a bit more complicated. You need a good filtration on it, and you look at the characteristic variety associated with D module, and it should intersect the hypersurface transversely or something along this line. I don't precisely remember. But it's a bit more complicated to state.
Any other questions?
So you already said that in your home DDP to O, you could also replace DDP with something else, with another D module. Would it still have an interpretation in terms of differential equations?
Not probably. So I'm not an expert in differential equations, but perhaps distributions is something one can plug in there. I'm not. Maybe correct me if I'm wrong. But in general, one can take abstract D modules, construct just like theory of modules over non-commutative rings, and plug in any modules there, and you will have a statement.
Any further questions? Maybe I have a somewhat naive question. So when you come from the area of differential equations, you're used to the idea that, say, under reasonable circumstances, given the initial conditions, there's existence and uniqueness of solutions. So then these theorems, to the non-algebraists, look very plausible, but it's probably more than just a restatement of this fact. So where are the essential difficulties in this program? Beyond, say, just the mere correspondence between initial conditions and solutions?
Do you mean in terms of its scope, or do you mean how far the statement is from the...
So is it more, it's presumably more than just a restatement of what people do in differential equations?
So the first bijection I stated, it's exactly the same statement. There's no difference whatsoever. But once we have such a statement in terms of D modules, one can replace the D modules that will solve one differential equation by But the original statement is absolutely a restatement. I think there's nothing interesting going on there. In his
okay.
master's thesis, he also writes that reformulating Cauchy-Kovalevska theorem.
It's more like a starting point for an algebraic theory.
I think so, yeah.
Okay.
That's my understanding.
All right. Thank you. Well, if there are no further questions, then let's thank Yajna again. And then it's my pleasure to introduce the third speaker, Raf Bocklandt, who studied and also did his PhD in Antwerp. Now he's in the Netherlands. I guess many of you know him because he's editor-in-chief of the Nieuw Archief voor Wiskunde, the beautiful magazine of the Royal Mathematical Society. But in real life, he works on representation theory and other complicated topics that he's going to tell us about. He has a book recently published with Cambridge about homological mirror symmetry, and that's presumably somewhat related to the subject matter of the talk. And you're also working on a popular book, or well, but at least say more philosophical or historical book on what is the journey through space and time.
It's about the history of geometry through, well, spaces and time.
Very good. Well, the floor is yours, Raf.
Okay, thank you very much for the invitation. So, I'm, as you see, I'm going to talk a little bit about mirror symmetry, but what I'm going to do is tell a bit a history of sheaf theory, because that's also one of the aspects of Kashiwara's mathematics. He brought sheaf theory into analysis and made a whole toolkit available that can be used, and this enhanced the field of algebraic analysis. And so I'm going to tell you a bit what is a sheaf, how was it invented, what was Kashiwara's contribution, and how does it lead to mirror symmetry and what that may be. Okay, so it's in 3 acts in different places along the globe. So let's start. And the first act is, we start in World War II in Edelbach, which is now it's in Austria, and it's actually a prisoner of war camp. And so it was a camp where the officers from the French army, when the Germans invaded France, they took a lot of prisoners, so officers, they captured them, and they were all put in a prisoner of war camp. And so you might think, yeah, if the situation in a prisoner of war camp might be quite harsh, but for officers, they had the luck that they fell under the Geneva Convention, so they were not allowed to do hard work there. So actually, they were imprisoned, but they had a lot of ample time to spend. So what did they all do there? Well, one of the things, that you can still look is, they made, for instance, a magazine. Just like I'm editor of the Nieuw Archief, they made Le Canard Engagé, which is, it's a pun in French, think a bit about it. KG stands for Kriegsgevangene, but engagé also means something else in French. So they made a magazine where they did all kinds of stuff. They wrote articles. Actually, there's an article about Henri Poincaré, an article about mathematics, written by a certain professor, Jean Leray, who will feature here. So, and what they also did there was, actually, they organized a university there. So there were some professors there, and they thought, we just organize a university curriculum and people can study. And even later, after the war, degrees up to a certain point that were awarded there could be taken into account for real degrees in France. And you could even follow mathematics. There was a course called Calcul Differentiel, and it was given by Jean Leray, and that's the main, important figure in this part of the story. So Jean Leray, who was he? So he was a mathematician. He was born in 1906, and he died in 1998. He studied at the École Normale Supérieure, which is where a lot of the bright minds in France studied. And his main topic in mathematics was fluid dynamics. And he was, at the time, a professor in Nancy, but he was also a reserve officer. So when the war started, he had to enroll, and he was captured almost straight along because of the Blitzkrieg. And so he spent most of the time in captivity in Edelbach. And he actually became director of that prison camp university. And after he went to the Collège de France in Paris. But he was a professor in fluid dynamics, but he didn't want, so when he was at the prison camp, he wanted to do mathematics, but not fluid dynamics, because that might have applications. So instead of doing fluid dynamics, he wanted to study something very, very abstract. And he thought, well, maybe I can do some algebraic topology. And doing that, so he taught a course on algebraic topology there. And in the meanwhile, he invented something called sheaf theory. And that's what we're going to talk about. Okay, so sheaf theory, it's kind of an abstract framework that can be applied in many situations, and it's a bit about the following situation. It's all about gluing. So here I have one graph on a paper, and here I have another graph on a paper, and I can so I can match them up like this, and then I get a big graph on a bigger paper. And so that's something that very often happens in mathematics. For instance, if you want to solve a differential equation, you can try to solve it on just a small piece of the space you're working in, and then on another piece, and then you might say, oh, maybe they glue together, and then I have a solution for a larger piece, and maybe if I can cover my whole space, then I can find one big solution, for instance, that everything glues together like this, and then I have like a graph on this space called, it's not so easy to do. So I have a graph with a base on the circle, so it's a graph on a circle. And so that's the basic idea, so the idea is that this thing of gluing things together, that gives rise to sheaf theory. So this is actually this is actually the paper that he wrote about it in the prison camp, and then it got published in the Journal de Mathématiques Pure et Appliquée. So as I showed you, what is a sheaf? You can glue solutions, and you want to abstract that. But there might be a problem, so I showed you a case where it kind of worked. So I glued things together, and I got everything on circle. So now let's try to glue this together on a circle. I have a problem if I go around. The two ends do not match up, so there's not a global graph, but you can piece local graphs together. And that's actually what you want to look at. Because so studying these things tells you something about existence of solutions or not, or obstructions to making solutions. And so the point is that it all depends, the behavior depends actually on which kind of graph paper you're working on. So here we're working on a cylinder, but you can also think of maybe I draw my graphs on a Möbius strip, and then I get different solutions. Or maybe I have something where I only look at the solution in one point. So, and then it's a completely different kind of thing. But all these situations, these very different situations, they're all part of one general theory, and that's called sheaf theory. And so the idea is, it's called sheaf theory. Why? Because, the English word for a sheaf is actually a sheaf in agricultural terms is just like some stalks of grain bundled together into a sheaf. And so you use that terminology here. These are the stalks, and they're grouped together. And then I have different sheaves. So this is a cylinder sheaf. If I glue them together, like, and take a longer paper, that makes it easier. So if I glue them together with a twist, then I get a Möbius sheaf. And if I only have one little stalk, then it's called a skyscraper sheaf. So this is a little skyscraper sheaf. And so each of these sheaves has different properties. And to measure these properties, there's this toolbox called cohomology. And Leray also developed methods to calculate this cohomology. So he really developed a toolbox to work with it. So why would you be interested? So you might think, okay, I'm only interested in graphs, so I will always graph things on a piece of paper like a cylinder. Why would you ever want to draw a graph on a Möbius strip? Well, if you're a mathematician, of course, you think that's fancy, but it's also something very practical. For instance, well, this is just on a circle, but think on a globe. So one of the things you can draw on a globe is maybe wind fields. So if you look at the wind directions in every point on a globe, then you actually draw a graph in a certain sheaf, which is called the tangent sheaf on the globe, because the wind is always tangent to the surface. So in each point, you actually draw an arrow of the wind direction, which is tangent to the globe, and the whole wind field is a graph on this tangent sheaf, which is 4-dimensional, because the sphere is 2-dimensional, and the tangent field is also 2-dimensional. So you got something 4-dimensional, and the question is, well, is this just ordinary wrapped like a cylinder, or is it wrapped like a Möbius strip? And what's the difference? Well, for a Möbius strip, there's an easy way to distinguish a Möbius strip from a cylinder. If I draw a graph on a cylinder, I can draw like a graph which is always above the 0 line. But if you draw a graph on a Möbius strip, then because there's this twist, your graph has to go under, it has to cross the equator once. So it has to become 0. And exactly the same thing is going on the sphere. So there's this theorem called the Harry-Ball theorem, which says that the wind speed must be 0 somewhere. And the reason is that the tangent sheaf of a sphere is not like a cylinder, but more like some kind of Möbius strip. So this kind of study is quite important because it can tell you something about behavior of certain fields or solutions. And so that's why Leray was also interested in that. So where was it used? So when Leray got back from the prison camp and published this, well, at first it was not really used in analysis, but its first uses was in algebraic geometry. At that time, France was a hotbed for algebraic geometry. You had Grothendieck, the most famous and enigmatic algebraic geometry there was. He was in Paris, and he used actually sheaf theory and a lot of other tools to transform algebraic geometry to something that people would not recognize at the time that it was algebraic geometry. It was completely transformed into something more abstract, and sheaf theory was an important part of that. But we will not tell this story, because that's the story of Grothendieck. We want to move to the second act, and we want to go to Nice and Kyoto, where we will meet Kashiwara and his collaborators. Okay? So Nice and Kyoto, so there's a Japanese-French connection going on that I will explain. So we have to first go to the godfather, actually, of algebraic analysis. So before Sato, analysis there's always a bit of a tension between analysis and algebra about how to find solutions. Algebra want to find maybe exact solutions, and you look at the structures of the solutions, and analysis is more like approaching solutions, but you can also try to look at the structure of solutions and look at the symmetries there and how they paste together, and that's algebraic analysis. And that was initiated by Mikio Sato. He was born in 1928, and so he was 12 when the war started, and he had a very miserable time during the war. So his father couldn't work, and he had to actually take care of the family, even after he was the oldest of the oldest son, and he had to take care of all his younger siblings. And so he worked actually as a high school teacher while studying mathematics and physics. But he actually, so he later, became a professor, and he also gave a talk at the ICM and in Nice. So that's where our connection with Nice comes from, about his algebraic approach to analysis. So he later became a professor in Kyoto, and he actually visited Nice several times after that as well, together with Kashiwara and Kawai, which were two of his students. So what was his contribution? Well, he started with inventing some new kind of generalization of functions, so called hyperfunctions. So probably some of you have known of the Dirac delta function, which is the famous function which is not a function. So it's zero everywhere except at the origin where it's infinity, and so it's a nonsensical object, but you can make sense of it in different ways. And the normal way we see it at the university is using distributions, and that's kind of the analysis approach. But you can also see it as, I'm not going to, so it's also, you can see it as some boundary problem for complex functions, and that leads to sheaf theory. And that's what this contribution of Sato was. And so that's how it all started with algebraic analysis. So finding a different way to comprehend the delta function. So as I told you, one of his students was Kashiwara. He studied first in Tokyo, and then he did his PhD in Kyoto while Sato was there, and he also became a professor there. He is famous for many things, so I will focus on algebraic analysis. And the important thing is that he introduced the notion of microlocal support for sheaves. So it's a way to describe certain aspects of sheaf. And this was worked out in a very influential book called Sheaves on Manifolds, and that he wrote together with Shapira. And yeah, we all know he got the Nobel Prize, otherwise we would, the Abelprijs, otherwise we wouldn't have been here. And this is Pierre Shapira. He's a bit older. He studied in Paris, and he worked on hyperfunctions during his PhD. So he got there's the connection with Sato, and so actually they met up in Nice, and Shapira also traveled to Japan many times, and they became lifelong friends, Shapira and Kashiwara, and together they wrote this influential book, but also many other papers. So they are lifelong collaborators. And I now, let's show the book. It's the yellow book. Well, for mathematicians, you would say, well, yeah, maybe the yellow book is not a good name because all mathematics books are yellow. But yeah, that's how it's colloquially named. So it was published in 1990, but it was 10 years in the making, and it's the standard work for this kind of thing. And it's a whole toolbox. It's not an easy read, but it's very useful. So the key concept is microlocal support. And so in order to say something about that, what that means, I must go back to physics and say you something about phase space. So if you, for instance, if you look at the pendulum, as you know, if you want to describe a pendulum, it's not enough to know the location of the pendulum to describe its orbit, but you also need to know the velocity, or more specifically, the impulse. And so you can make kind of a space of all the possible states in which the pendulum can be, and so it will have an angle 2 pi from 0 to pi, for instance, that 0 to 2 pi that measures how far you are from the vertical line, and it also gives you the velocity, and so together this forms a space. And in this particular case, for a pendulum, it's a cylinder, because the angle can only vary on a circle, while the velocity can be whatever size. So it's an infinite cylinder, but in more complicated topics, in more complicated problems, it can be whatever big dimensional space you think of, but it's always even dimensional, because you always have this position and the momentum. So it's, and this, if you want to describe this mathematically, it's called symplectic geometry. We will come back to that. So, but phase space is an important mathematical concept, and what actually Kashiwara did, together with Shapira, was introduce kind of phase space into sheaf theory. So their idea was, so we want to, so as I said, so there are different kind of sheaves. So you have the cylinder and the cylinder and the skyscraper sheaf, and you see here, this looks the same if you move a bit. So this is what is called locally constant. While this, if you're over here and you go over and you go a bit to the left or to the right, the stalk changes; it becomes 0. So there's a behavior here that's not seen here. And to describe that, they invented this microlocal support, which is part of space. It's kind of morally, it tells you, well, if it gives you all the possible directions in which you can zoom, and the sheaf will change. And that's the microlocal support. So let's do this for a very easy sheaf. So I look at the sheaf on the globe, and I look at the sheaf of functions that are defined on the continent. So we say, so for instance, a function that's defined only on the continent, it's like population density, okay? It's always 0 if you're underwater, I think. And, but it can vary on the continent. So it's actually a sheaf that looks a bit like the skyscraper sheaf, but there are skyscrapers on the land and none on the sea, okay? And so what they did was to find a piece of phase space that gives you describes where the sheaf changes. So let's do that like here. So I took two pieces of the globe. So I took a piece of Africa, well, 2 pieces of Africa actually. So there's a piece of West Africa and then a piece of East Africa near Madagascar. And so the idea is that this microlocal support gives you the co-directions, like you should think of the directions where it will change. And so the co-direction means like the direction of the wave front. So you think of a wave moving in that direction, and if it drops off the cliff of the shore, then this is the microlocal support. This direction is contained in the microlocal support. So it's kind of the normal to the coastline over here. But of course, if you have a very small island like that, then you drop it in every direction of it. It's like just a single skyscraper, a single stalk at the point. Then the microlocal support will contain all directions. Okay, so it tells you the directions in which it changes. And what they proved is, and this is the big result, that this microlocal support cannot be just anything. Okay, it cannot be too big. So they showed that it's co-isotropic, which is a technical term, and if the sheaf is constructible, then it's Lagrangian. And this means actually that the dimension of this microlocal support cannot be too big. It can be at most half of the dimension of phase space. So it's a small part of phase space. But the important thing is that they prove this for all kinds of sheaves. So it's a very powerful theorem because it works in this complete generality. Okay. So this is a major part of this book, Sheaves on Manifolds. And now I want to move to the third act and tell you a bit about things that I do research on, which is mirror symmetry, and tell you a story that took place somewhere in the end of the 2000s, so 2008, 2009. And we moved to Northwestern University, which is a university near Chicago. And I'm going to talk about two other mathematicians, David Nadler and Eric Zaslov, and they are, they study things on the boundary between physics and mathematics, and related to a very important theory from physics that maybe failed in physics but transformed mathematics, and that's called superstring theory. And so superstring theory, basically it says that elementary particles are strings, and they move in space. But what's a string? Well, the strings comes in there are two possible strings. There are closed strings. The blue ones, they loop, they form little loops, and they move around. But then you can also have open strings, and they have two ends. But then if you want to describe them, these ends, they cannot just wiggle about. They have to be fixed to something to make a valid theory. And that's what they call branes. So they have to be attached to branes. And string theory studies the interaction between these strings and these branes. It's very complicated. So what you do, if something is too complicated, then you simplify it. But there are different ways to simplify this complicated string theory. You can focus on different aspects of the theory. So you can either focus on symplectic geometry, that's the phase space kind of thing, or you can focus on the algebraic geometry, and that's the theory that Grothendieck, the same guy, as we saw a couple of slides ago, but now in a more, hermity kind of, so Grothendieck left mathematics and became a hermit, and this is a famous photo that a lot of mathematicians will recognize. So you can focus on different aspects, and this gives rise to different theories, 2A and 2B. What they are precisely, it's not so important. But the idea is that you could at least do some, you could actually calculate, calculate things. But the point is, these are calculations, and these are calculations, and they give different results. But what physicists know was that, well, if you do calculations A in some universe, and they might correspond to calculations B in a different universe, and vice versa. So this was really strange. They didn't know how that happened, but they could use it to do calculations that mathematicians could not do. And mathematicians at first, they were a bit okay. These physicists, they do all this strange stuff, but they make up answers that are right. So there must be something going on, and that gave rise to mirror symmetry in mathematics. And one of the ways to do this, so the idea is you want to understand these categories. So the idea is that, category is behind the picture. So the idea is mathematicians do these theories, they describe them using categories, and if they match up, we say the categories are equivalent, but the categories are notoriously hard to calculate. And how to work with these categories, so the categories of coherent sheaves in algebraic geometry, they are better understood, but these Fukaya categories, they were notoriously difficult to understand. And what happened was that actually this David Nadler and Eric Zadlov, they used this toolbox of Kashiwara to actually interpret the Fukaya category in terms of this microlocal support. And then it became very understandable. At first they did it for the cotangent space, and that worked really nice. And then later on, a lot of other people used this toolbox to extend it so that now we can study these Fukaya categories. We understand them a lot better, and we can work with them in many, many other places. So this thing that Kashiwara originally developed for algebraic analysis actually has a lot of applications in a lot of other fields, and this is a nice example of it. So I will conclude my talk with this statement. So microlocal support for sheaf has become an indispensable tool in many areas of mathematics. There used to be a statement by Alan Weinstein, who said everything is Lagrangian, but I would tweak it a little bit. The conclusion of this talk is that everything is microlocal. Okay, thank you.
Thank you very much, Raf, for this truly flamboyant talk. Let's see if there are any questions. That can't be.
Yeah, Emma.
So, do you think Kashiwara himself, how far is he from this? Would he understand much of this? Or
Well, maybe not the details of Mercy, but he has contact, so he knows of Nadler's work. And also David Nadler gave a talk on the day of the Abelprijs in last year, where he explained some of the stuff and the relations with him. So he's definitely aware of it.
Any further questions? Well, if not, maybe I may ask you a question. You started with Leray, who is truly a towering figure in Navier-Stokes and fluid dynamics in general. And I can testify, I've been in many conferences where people start their talks with just pointing out just how important Leray was for fluid dynamics, but they never mentioned sheaves. And so you brought us all the way to mirror symmetry and superstring theory. So is there a way back somehow? Can the community in fluid dynamics in the end use some of these toolboxes and arrive at insights that are more algebraic in nature?
Well, I think, I'm not a fluid dynamics person myself, but I think Leray developed this idea of sheaves with also this analysis with in mind that you paste together solutions, and that there are obstructions. But I don't know how easy you can apply this to fluid dynamics itself, because usually maybe, I don't know, the topology of the space on which you consider your fluid dynamics, I don't know how much it gets into the problems people from fluid dynamics study.
Arnold has some very geometric work on fluid dynamics. So I was wondering if there's maybe some connection there, or
maybe I wouldn't know.
Okay. All right. All right. If there are no further questions, then we thank our third speaker, Raf. And that brings us to the second part of this evening, which is a panel discussion with the three speakers. So may I ask the speakers to take their places in the panel? And it took some effort, but I convinced Eric Opdam to moderate this session, because Eric is a first-hand specialist also in the subject areas of today, much more than me. So I think we get a very nice discussion if Eric does this. So Eric, please step forward and take over from me.
Thank you.
Yes. Thank you very much, Yajna and Geert and Raf, for beautiful talks on a very complicated subject. I was thinking what will add something to the experience, and I thought, well, you gave talks, 30-minute talks about these very difficult topics. Kashiwara's work is vast and very deep and very conceptual, so that must be very restrictive in terms of what you can say and what you can do with that. So now I would like to zoom out a little bit and look at the impact of this vast body of work and the high quality of it. It must have serious impact in mathematics and maybe also in physics. And I would like to invite you to reflect on that from your perspective. So maybe, Yajna, I will start with you.
Yeah, let's see. I think one of the things that I didn't get to talk about was the singularities. Seems like a priori completely unrelated to Kashiwara's work on D modules, but they are used specifically because of these microlocal supports, like where things should jump. They also remember things about singularities of spaces. And there's something called the Bernstein-Sato polynomial, where Kashiwara also has contributions. They are specifically designed. They arose from differential equations again. Like you take a power of a function and try to derive it. That gives you some formula, but power is always an integer. So if you try to analytically continue it with complex numbers instead, there's some polynomial that arises that's called Bernstein-Sato polynomial. Was already studied by them, probably for other purposes. But now this has become one of the most studied thing in singularity theory. For instance, Kashiwara proved that it has rational solutions. Only rational numbers can be its zeros. And we know that if this polynomial is linear, then the hypersurface must be smooth, which I think is one of the most incredible results.
Thank you. And you had this beautiful scheme towards the end of your talk, where you explained that, it has implications for Langlands, for the Langlands program, and you mentioned mixed Hodge modules. All these things sound very exciting to me, and it was way too quick for me to understand anything about that. So could you add a little bit to that?
Yes. So maybe I can say some things about Hodge modules. So it's a bit scary to say that I can say some things about Hodge modules. Perhaps one way to, again, it's motivated by singularities, that if we let's say understand very well how smooth spaces work, and then we want to understand a family, like a smooth spaces, a collection of them in varying continuously in a family, very, very naturally singularities might show up, that it gets degenerated into something singular. And for a long time, so various topological invariants like cohomologies are important, and we kind of understand how they vary in family. As soon as singularities appear, things get quite complicated. And for a long time, theories that Hodge theorists did for variations of Hodge structures, we could only understand when we approach a singularity in one direction, so when it's like one parameter degenerations. So if the singularities appeared, if we are studying something over a one-dimensional family, one-dimensional base, like the circle, then people knew how to understand, how to approach this singularity Hodge theoretically. What these Hodge modules allowed us to do, or Moriko Saito's theory, is to be able to do that or maybe regular holonomic D-modules, which is the work of Kashiwara, gave us a way to sort of even talk about what would mean to approach a singularity from a higher dimensional, like from various directions all at once. So I think this is probably at least most useful to me, that this theory exists now, that one can talk about how cohomology is degenerate, and one can study that on arbitrary base.
I see. Okay, thank you. So then, thanks a lot. So let's go to Gert. So Gert, of course, you are a specialist in also in harmonic analysis, and I know that Kashiwara's work has relations to that. So I'm very curious to hear your perspective on the main impact of that work of Kashiwara.
Yes, so in the what they wrote about the motivation of giving Kashiwara the Abelprijs is algebraic analysis, and I think that the Japanese school of Sato and Kashiwara Kabai is really the complex analytic point of view. So you have the real picture, say, Remonder, PDEs, and you have symplectic geometry. You have the beautiful work of Duistermaat-Gilliman about relations between spectral theory of elliptic operators and closed geodesics and links of those. That's all a real story. Now you can complexify real space, and that I already mentioned in my lecture, that Riemann made that point very clear, that you get an enormous amount of insight. And I think complexifying space and doing it in a complex analytic way was one of the motivations of Sato, and later in the work with Kawai Kashiwara. And then, of course, you can go further, and then, in fact, in most applications, it's in fact algebraic geometry, because if you just if you complexify your real space, it's like a tubular neighborhood around the real space. Whereas in algebraic geometry, you really have very precise meaning of asymptotically at infinity. You have the whole apparatus of algebraic geometry. So in a sense, I was surprised when I noticed that Kashiwara was awarded his Abelprijs for algebraic analysis, and the name of Joseph Bernstein was not there, because he did, I think, equally well profound work, more in the algebraic geometry direction, and Kashiwara more in the complex analytic. Of course, they both are extreme. They've done outstanding work in the representation theory of semi-simple algebraic groups. For example, the Kastan-Lustig conjecture I mentioned was solved by Kashiwara, and Brilinski was solved by Bernstein and Beilenson as well. So I think there was a wall in Berlin separating the West and the East. Yeah. And so the communication was difficult, but the Russians were allowed to write short papers, and then they came through. But Japan was an island, and somehow in a separate... And then later, of course, Kashiwara did also important work, like you mentioned, rationality of the roots of the B function. And so, yes. So these two things came together. But I wanted to make that point here.
Okay, wonderful. Thank you. Raf, your take.
Well, yeah, for me, so I'm originally from representation theory of quivers, and so it's very algebraic and quite far from analysis. But then when after my PhD, I moved to this mirror symmetry, and it's a duality between, on the one hand, algebraic geometry, and on the other hand, symplectic geometry. And I was always very afraid of the symplectic geometry because it was so analytic, and I could not make much sense of it. But then using this toolbox and this later work by Nadler and Zaslov, yeah, for me, then it made a click, because then suddenly I could translate a lot of these things from analysis that actually I was very uncomfortable or that I did not understand, and then I could translate it to things that I was a lot more familiar with, these constructible sheaves and all this kind of the derived category and all these things. So for me it was like very influential. That it made my life a lot easier, because otherwise I wouldn't have understand much of the things that I was studying.
Okay, thank you. So let me have a look at the time. Yes, so perhaps, of course, I also would like to give the audience ample opportunity to interact with the speaker. So maybe let's now go to the audience for questions. Ike.
Thank you. The question was posed whether our Abel laureate was aware of the work on mirror symmetry. But he has changed fields quite a bit, and I believe he's still extremely active, working with a group of North Koreans on quantum algebra and categorification. I think it could actually be more your field than... could somebody say something about this?
I don't know, so I'm happy to look at our panel. You have any knowledge of this?
I don't have.
No.
Okay.
I'm sorry, Ike.
For the next time.
Okay.
Maybe in answer to Jan van Eerver's question about fluid dynamics.
Yes.
These fluids flowing over a surface form a foliation, could have many singularities, but the space of flows is studied with a lot of sheaf theory. You need sheaf theory to study the invariance, cohomological invariance of this space. So sheaf theory occurs in that form in foliation theory, which is some sort of fluid dynamics.
Right.
Yeah.
Right. Okay. So Jan is nodding. He message delivered. Thank you. Thank you very much. Other questions, or do you want to comment on what was said? No. So then let's look at other questions. Tom.
Yeah, analytic functions were very much emphasized, in particular in the second lecture. For instance, in D modules, is there also an approach where you just work with C-infinity functions, or is analytic functions really necessary?
Thank you.
In the statement of the theorem, again, I'm not a differential equation person. From what I understand, I'm not sure if I allow differential equations with C-infinity coefficients, whether a C-infinity solution should exist. I think the theory does depend on the analytic assumption, from what I understand, but I might be wrong.
Tom, the microphone is coming.
If you look at an undergraduate's introduction to differential equations, you see theorems proved where it's already sufficient that the coefficients are twice differentiable. Yeah.
Yes.
So
yeah, it's possible. Yeah.
Thank you. Perhaps Gert or Raf, you have ideas
well,
about
I
this
think it's really about analysis, about the analytic or algebraic category. With Bernstein, it was you take a polynomial to the power lambda, a real polynomial, and lambda is a real number, then it's a tempered distribution. And is there an analytic continuation in lambda on Rn? And that was solved by Hermander first and by Atiyah depends on the singularities of that polynomial, and then by Bernstein in a very algebraic way, and I don't think those arguments work in the C-infinity context. No.
So the generalization that Kashiwara made was, in the end, was mostly applied to the context of a complex algebraic geometry. So with complex analytic functions. So that,
would the wind field also be analytic?
which
You were having a station with the wind field. Should it also be analytic?
what?
I think that was Raf.
On your first slide.
Oh,
Yes.
that was you.
What was the question? Which field?
The wind.
Wind.
The wind field be analytic.
Yes.
Okay, yeah.
No, we don't believe that. It's rather chaotic.
It's okay.
But if we believe that it's tangent bundle, then it could be. Yeah, this is.
You can consider the tangent bundle as a complex tangent, but then the wind field, well, yeah, I think you could consider it as an analytic.
Other questions? So then maybe I have one more question. So it was mentioned several times that Kashiwara is a student of Sato. And Sato was this visionary man. He had really a huge impact in Japanese mathematics. And there were many, many great students of Sato who did wonderful things in various directions. Do you think Kashiwara is also a visionary figure in such a sense? And if so, in which direction do you expect him to have future impact? Yajna.
So I'm not super aware of Kashiwara's current field of research. However, I do think that this concept of regular holonomic D-modules and all the theory that he developed in that direction, from my perspective, it feels visionary indeed. Without that, we wouldn't have Hodge modules today. So I find that pretty incredible.
Well, I think Kashiwara did absolutely great work in the 70s, 80s, 90s. But for all mathematicians, there is some point that things go slower. But you mean visionary from the work he did in the 70s or still now? I don't.
No, so I know that recent conceptual progress on the question of the unitary dual for a reductive group is based on his ideas of localization, turning representations into equivariant D-modules, and then looking at the Hodge structure, the Hodge filtration there.
Yeah.
And this was long conjectured, and it was completely stuck, and now suddenly things are moving. So that is for me, because I am a specialist in that field, so for me it is extremely exciting.
Yeah,
so
yeah. But these use the techniques developed by Kashiwara, you mean?
Yes.
But this is not recent work of Kashiwara. No?
It's not recent work of Kashiwara, so that was not the question. Okay. No, the question is, do you see some future direction where it will have further impact?
Well, I think the field of algebraic analysis is extremely important.
Yeah. Raf?
Yeah, but I think he's also, he's done also a lot of other things that we didn't touch upon. That's maybe also nice to see, like the work on crystal basis,
quantum groups.
which is actually, quite far from the things it's a complete different direction than the things we discussed. And he also did very important, so he's quite broad, actually.
Yeah, he is.
And that, I think that's one of his strengths.
Yeah. Okay.
I think also like this theory is now being generalized to other fields, not just complex numbers, and having deep impact there. I think his work that has already been done is having a lot of influence already, still now.
Yes, true. Yeah. Okay. So I don't think that there is a pressing question. So then I'm happy to say let's go for drinks, but first Jan will close the evening. So.
Thank you very much, Eric. Yes, indeed. Let me first thank again the three speakers for the marvelous journey that they offered us through Kashiwara's work in algebraic analysis. But before we go to the drinks, I also want to say a word of thanks to the Academy of Sciences, who's hosting this wonderful event. Ella, who has been the driving force in the background, organisatorially, all we have to do as organizers. So we take the honor, but it's not true. We just come up with a good list of speakers, and all the other work is done by Ella and the fantastic staff supporting her. Emma, who is there for the technique, people over there that we can't see who are recording this. It was a very smooth event. Everything went very well. And now we're looking forward to a drink. So thank you very much.